Hey there, grade 12s. We're going to go through briefly the theory about the different factors that affect the rate of reaction and how fast it occurs, and different ways it can speed up or slow down. So it seems like there's a lot of learning objectives here, but there's not that many. They're all connected together. So we'll start off with the 5 factors we'll study that can affect the rate of a reaction, and we'll look to explain how each of those affect the rate theoretically, so what the particles are doing. We'll be able to state the collision theory, look at reverse and forward activation energy. It's a new term that determines if a reaction will proceed, and then we'll apply that to potential energy diagrams in different ways. Lastly, we'll talk about what the role of a catalyst is in a chemical reaction, and then we'll interpret it's a type of normal distribution that describes how many particles are capable of reacting, and we'll look at that as a way to interpret the patterns and the probability. So an example to start off, why rates are important, is on the farm. So a grain silo is a tall tower that you see there, and it's filled with very fine powder. So we're going to see how the state of a material that's being stored affects the rate that it reacts. If there's a spark in a grain silo, even though it's just grain and kind of dried up grass, there will be an explosion or a big problem with that. And the reason is that an individual piece of hay burns very slow, okay, almost like a piece of paper. But when it's ground up as a particle, it has a higher surface area. So all of those particles react at once. There's a rapid release of gases and energy, and it leads to the explosive result. So even though it's the same reaction, the speed that it happens at can determine the outcome and the effects that it has. So the rate of reaction occurs, that depends on many factors, which we'll summarize coming up here. Number 1, concentration. The higher the concentration of a sample, the higher the rate will be, because there's more particles colliding. And you'll see this term over and over again. There's a greater probability. It doesn't mean that they'll all collide more often. It just means there's a higher chance. So if you look at the image on the right and on the left, we've got figures A and B. Right? In figure A, there's fewer particles in this sample, so they have to kind of make their way through all of the other particles that are not reacting. And there's a higher chance it reacts or it bumps into something that's not part of its reaction. In B, where there's a higher concentration in the same area, there's a higher chance that they'll collide with the red and the blue circles, leading to a reaction. Surface area is the same idea. If we increase the surface area, it's like crushing up powder, and this increases the rate because there's more area for the particles to collide in. If the red particles are reactant A and the green particles are reactant B, in the figure on the left, I'll just split this in half, those particles can only access the outside surface. It can't access the particles buried deep inside that shape. But if it's crushed up, there's many different surfaces for those particles to react on, and now they're all paired up and there's none waiting around. Okay, so the higher the surface area, that means more like a powder, the faster the reaction will proceed. Increases in temperature increase the rate as well, and we've all tried this at some point in our lives. We want something to go faster, so we increase the temperature, whether it's cooking or manufacturing or making something. We have this understanding that higher temperatures mean higher energy, and we're right. So again, there's a greater probability for a collision because at higher temperatures, particles have more kinetic energy, which means they move more. And the faster things move, the more likely they are to bump into each other. Again, more likely and probability. So we're not saying absolute terms here. It's the idea that there's a higher chance of them colliding with each other. So an example, at room temperature, an alcohol will evaporate. But if a flame, which is at a higher temperature, exposes to it, the particles evaporate faster, and there's rapid expansion of the gas, which is similar to an explosion. So the temperature dictates the outcome as well. The products are the same as the reaction, just the fact that they're generated faster as an unintended outcome. So the nature of a reactant depends on the substance's reactivity. Okay, so this depends on the state that the substance is in, the type of bonds that are holding it together, and its general reactivity. So there's a link there that summarizes these nicely, but overall this varies based on the type of substance and the property that we look at. So putting this all together, you'll notice that was 4 different factors. We're going to look at catalysts in a bit, but we'll look at a concept called the collision theory now, right? And this is a theory of how molecules proceed in a reaction. And what it states is that a successful collision is what it aims to define. And a successful collision is where reactants collide in the proper orientation and with enough kinetic energy to break new bonds and form new ones. So let's look at those independently. Orientation refers to the way molecules collide, okay, or the sides of the shape of them that hit each other. The smaller the molecule, the higher the probability that it'll react with the proper shape because there's less faces to it. Bulky, irregular shaped molecules have lower probabilities because there's specific sites on them that need to react. And the bigger they are, the less chance that one site gets hit for a reaction. So if we examine the reaction here, 2Br and O as the reactants, they need to combine with each other to form bromine and nitrogen monoxide. So in figure A, it shows us that if the 2 bromines collide, they'll form that Br2 molecule, and NO will split off. In figure B, the bromine need to collide as well. So that's a successful collision because the bromines hit each other. This is a successful collision because the bromines hit each other here. This is not a successful collision in part C because the oxygens hit each other. So what we're being told here is that no reaction will happen and the molecules just bounce off of each other. Okay, so that'd be called an unsuccessful collision. So the orientation just tells us which atoms need to hit each other for the reaction to happen. It's kind of like the handshake, right? If we both go to shake with your right hand, it's a successful handshake. They match. But if one shakes with their right and one shakes with the left, the hands won't match up with each other. So here's a more specific example. If you look here, this states that this white molecule or atom needs to hit the double bond of this molecule. If the green molecule hits, there's no reaction. It's an incorrect orientation. If it hits on the side, no reaction. And if the white atom hits the other white atom, again, no reaction. So in this case, the orientation states the white atom needs to hit the double bond for this reaction to happen. Now, the second postulate of that is activation energy. So this is a new term for us, and we want to pay attention to what it represents. Even if particles collide with the proper orientation, not every collision will produce a reaction. They have to have enough energy or sufficient energy to break the bonds. And this is called the activation energy. So it's defined as here, the energy needed by the particles to successfully break the bonds, holding the molecules together. So even if the molecule collides in the right orientation, if it's not moving fast enough, it will just bounce off. Okay? So an analogy for this is a university application. A program sets a grade cutoff, right? You can have all the prerequisites, but if you don't have the marks high enough, you won't get in. And if you have marks high enough and the right prerequisites, you'll get in. But if you have high marks but not the right prerequisites, you won't get in. So there's 2 factors that affect that, kind of like activation energy and orientation. Orientation needs to be correct, and activation energy needs to be high enough for a reaction to happen. So those are the 2 factors that molecules need to consider, and that's why we stir things. The more we stir, the more likely we are to vary the way they collide with each other. So on a potential energy diagram, what we'll see now is a little bump in it. Normally, what we're used to seeing at this point is the reactants becoming the products, right? Or vice versa. If it's an exothermic reaction, the products are lower. Now in this case, what we're saying is this is not what actually happens. It's a little more complex than that. What we're going to take into account is the activation energy. So that's the amount of energy the reactants need to form something called the activated complex. So this is where all the reactants are bound together for an instant. It's very unstable, which is why it has high energy. Okay, so it's the highest energy point of a reaction. From there, it falls back down. Notice delta H is unaffected. It's still the difference in energy between the reactants and the products. for an exothermic reaction, there's a smaller activation energy, right? But it still leads to the activated complex. Okay, and we have an enthalpy change for that as well. So what the potential energy diagram is describing is the stages of stability that molecules go through. And that's what its potential energy is describing. The more unstable it is, the more away from the octet it gets, right? Or the more electrons that are in one area, the bigger the molecule, the higher the potential energy becomes. So molecules need to hit with the right orientation, like we talked about, and the right amount of energy. And that energy is called the activation energy, and we abbreviate it EA. Right? If they hit with the right orientation but not enough energy, no reaction happens. They have to get over this little bump here in order to react, and then they'll fall down to a more stable state. So in summary, this chart just compares the properties of endo and exothermic reactions. Reverse activation energy is just the activation energy needed to turn the products back into reactants. Okay, so you can make a note about that, and the rest we've talked about up until this point. So the activated complex, what is it? It's an unstable state, okay? It's where all of the molecules are bonded together. It breaks the octet rule, and it becomes unstable. So the instability means it has the highest energy because it wants to do something. High potential energy means that molecule is going to react or rearrange its bond. It won't just stay as it is. Low potential energy means that the molecule is stable and that it's unlikely to do anything. It will stay as it is. So here's an example of a transition state. So reactant A is at the top, and this is reactant B. What we're saying is that the oxygen and the carbon need to collide. So that's the orientation. Now, assuming they have the proper energy, for a split second, you'll notice that carbon has 1, 2, 3, 4, 5 bonds. Normally, carbon only has 4 bonds. So because this happens, this is called the transition state. It exists for a very small amount of time. It's unstable, and the bonds will rearrange themselves in the most stable way, which results in the products forming. So the reactants form a transition state, which lead to the products. And that's the case in all reactions. Right? So this would be the highest energy state in that reaction. This is also called the activated complex, which you were just seeing. So transition state and activated complex are similar terms used interchangeably. So if we look at an example for this, and you can pause now and try this. So what I'll do now is go through, if you've tried it for yourself. So a potential energy diagram has the potential energy off to the side here, and we're going to measure that in kilojoules. Right, and we've got reaction progress. We don't put time, just reaction progress, because it's not being scaled. So we're told that the reaction is between nitrogen and oxygen to produce nitrogen dioxide. I should write a reaction, right, and balance it. 2 here and a 2 here, so that I know what I'm working with. Right, we're told it's an endothermic reaction, which means the reactants are lower than the products. So there's an activation energy of 150 kilojoules, which means there's going to be a little peak. Right, again, that peak comes higher, right, and we can just label it as is. So EA equals 150 kilojoules. We'll label the enthalpy change here as 114 kilojoules, right, and that's positive because it's endothermic. We've got to raise the energy of those reactants up, and it's customary to write the reactants on the first line and the products on the second. Okay. Now you'll notice there's a little bit of a gap up here between that there. That's called the reverse activation energy. So again, to turn the products back into the reaction, and you'll notice that it's the sum of delta H and the activation energy. So if we subtract those two terms, in this case we'll get 36 kilojoules. So that's a properly labeled potential energy diagram. It has the activation energy, okay, from the reactants to the top of the activated complex, which is up here. That's that transition state where everything's bound together. That's the activation energy. So proper orientation, proper energy, and we'll have a successful collision. That's the purpose and the postulates of the collision theory. So what we use that for is to describe the likelihood of a reaction happening under certain conditions and for comparing it. So if we would like to compare conditions of a reaction, we can identify if it will speed up or slow down based on what the particles do. So we'll talk about now, lastly, this is the fifth factor, right? We skipped over it, but a catalyst. So if you've studied biology, you've learned what a catalyst is. It's a substance that increases the rate of the reaction without being consumed. So a common catalyst is used in the breakdown of hydrogen peroxide. It's manganese dioxide. Hydrogen and oxygen. Okay. Normally this is the reaction here. Let's change that. Water and oxygen. So without the catalyst, right, notice how it's written over the arrow. That signifies that it needs to be there, so it's a reaction condition, but it doesn't participate, so it's not part of the balancing of this. Right, so if I put a 2 there and a 2 there, that'll balance everything out. Okay. So what they do is they provide an alternate mechanism for the reaction, so it changes the transition state a little bit, and it lowers the activation energy. So it's the same reaction in the same product, just faster because more molecules can collide at once. So here's how the potential energy diagram changes. Notice how the reactants and the products are in the same spots. Delta H is still the same, there's no difference there. The only thing that changes is the activation energy at the top is now smaller. So a catalyst reduces that. And by having a lower activation energy, there's a higher likelihood that more particles can react. It would be the equivalent of a university lowering its admission mark. We've done nothing to the molecules or the people in this case, but by lowering the admission mark, more people are able to apply. Right? And by lowering the activation energy, more particles can react. So think of the activation energy like a particle's grade and what it can do with it. Right? And that's really how a reaction determines if it happens. So in practice, there's two types of catalysts. A heterogeneous catalyst is one that's in a different state than the reactants. Example, if you're doing a gas reaction using a metal catalyst, right, they're in different states. And then a homogeneous one is where they're in the same state. So aqueous sulfuric acid catalyzes aqueous alcohol reactions. So they're both AQ, which means they're in the same state. Right? And that's just a classification. So one last effect that we'll look at is the temperature of a system, and what you're looking at here is called the Maxwell-Boltzmann distribution graph. And what it describes is the number of particles that have the correct amount of kinetic energy to react. So notice that number of particles is on the y-axis here, okay? And kinetic energy is at the bottom. So the higher the kinetic energy gets, the lower the number of particles that have it. Right? It's like the average in any class. Most people fall somewhere in the middle, right? Which is not enough kinetic energy. Only a small section of particles that have the kinetic energy and forward are able to actually react. The rest of the particles, which you see is most of them, right? If we look on that there versus those points there, right? Most particles don't have enough energy to react. So what we do is we try to add energy to them, right? And by giving them more energy, we help them reach that activation energy, right? So it'd be like giving yourself a couple of extra marks to reach a university cutoff. You don't change the cutoff, but you kind of give yourself a boost there. So this shaded area represents all particles that can react. And the unshaded area represents the particles that cannot react. Right, so just pay attention to the graph. The lower it gets, again, no particles have zero kinetic energy. They all have some. Most particles have an average amount, and maybe a third of particles in a sample right off the bat have enough kinetic energy to react. And again, this kinetic energy helps determine if they can reach the activation energy or not. So pay attention to the axes on this point. So as the temperature changes, right, and this is just a summary of what happens in a reaction, right? If we look at a low initial temperature and a high secondary temperature, what we've done is we've changed the number of molecules that react. So pay attention to the shaded part of the graph here. Initially, the shaded part, right, there's very low number of particles, right, and this corresponds over here. Low number of particles that can react, that shaded area. When you raise the temperature of a sample, it doesn't change the activation energy. It's still fixed at this point. But what you do is you give more particles enough energy to react, so the shaded area increases. And what that represents is a higher temperature, means more substances have more energy to reach that cutoff. And this would be the equivalent of you getting a boost on your applications. Right? If we added 10% to everybody's mark, we don't change the cutoff, but now more people can apply to the same program. Okay, so try to think of it in terms of that. So what you'll want to do is summarize the effect of a catalyst. How would a catalyst change the Maxwell-Boltzmann distribution? Right, and just as a summary, if you have gone over that, with the number of particles here and the kinetic energy down here, if we draw a simple normal curve, right, there's our activation energy normally. A catalyst lowers the activation energy. Right, we call that the activation energy of the catalyzed reaction. So what happened here? We didn't change the particles. All we did was we made it easier for them to react. And to continue with the analogy, if we didn't change your marks but we lowered application averages, more people could get in as is. Okay, so this graph just describes the overall distribution of particles that can react. Hopefully that helped clear a few things up. There's some homework questions to try there, and good luck. Thanks for watching.